energy chapter. So we introduced the energy, and we said there can be two types of energy, right? Mechanical energy, kinetic energy, and so we have kinetic energy and potential energy. But before we come into the energy, these two mechanical energy, we also talk about work, right? Um, energy, you can say the ability to do work. Work and energy are connected. We said force will do a work. If we have a force, that we can use that force to do work. And if the force is a constant force, the work done by that force is force parallel component of the force along the displacement multiplied by the displacement, right? So you need to take the parallel component of the force parallel to the displacement, multiply the displacement will give us the work done. And if you look at the unit for the work done, it will be Newton meter, and we call it joule. Okay, the work has the unit joule. So does the energy. So we can already see the connection, the work and energy are related. So we then defined, please sit down, kinetic energy, right? So when a force does work on an object, its kinetic energy will change accordingly. If the work done is plus 100 joule, its energy, kinetic energy will increase by same amount, 100 joule. If the work done by the force is negative 100, then the kinetic energy will decrease by 100 joule. So then of course, we define the kinetic energy. Sometimes I use this, sometimes I use this, is equal to half mv square. So you should know these two equations, and you should know how to get the parallel component. The parallel component will be f cosine theta, where theta is the angle between the force and the displacement. Theta is the angle between the force and the displacement. So we can see from this equation how the work can be negative, because when theta is equal to 0 to 90, cosine theta will be positive. So if the pushing is in the forward direction, okay, then it doesn't have to be exactly parallel. Anything from 0 to 90, displacement and the force are more or less in the same direction. So you'll have a positive work. But if the theta is greater than 90, 90 to 180, the cosine value is negative, the work done will be negative. So it will be the work done will be negative. So negative work will decrease or take the energy, kinetic energy out of the object. A positive work will be provide the energy into the object. So that is basically, what we've done. Then we went to potential energy. So potential energy is energy that is due to a conservative force. So like when you drop something, you see all of a sudden which had a zero kinetic energy, when it dropped, its speed is increasing. That means kinetic energy is increasing. Where is the energy coming from? Our normal answer is because force is doing work. What is the force? The gravitational force. It is doing work. So it is being pulled, moving certain displacement. So you can say it is coming from the work done by the gravitational force. But we like another approach. We will say no, it's not about work or anything. We will put introduce something called potential energy. We say when it is coming down, the potential energy due to the gravitational force, we define it as some potential energy. It decreases. There, where is it going? It translate or transformed into the kinetic energy of the object. So then, we get the equation for the potential energy due to the gravitational force. It is equal to mgy. M is the mass of the object. G is the acceleration due to gravity, which is in SI unit 9.8 meter per second squared. And Y is the position of the object relative to the Earth, okay, because Earth is the one providing the gravitational force. So you can put the Y equal to 0 relative to the Earth. It can be anywhere it can be on the surface of the Earth or maybe at the center of the Earth. It doesn't really matter. You can choose Y equal to 0, say for a book sitting on the table. You can put the Y equal to 0 at the table, or you can put the Y equal to 0 at the surface of the Earth, or you can put the Y equal to 0 somewhere even above the object. It is somebody's choice. Okay. Y is arbitrary. Arbitrary mean it's not fixed. It's up to your convenience. So, but it's a vertical position, only the Y coordinate. It doesn't depend on the horizontal coordinate. It only depends on the vertical coordinate, and Y is measured positive upward. That's very important. You should remember Y is the vertical coordinate and positive direction is upward. Then only the equation is mgy. What we are normally interested in is not just the absolute value of the potential energy. The change in the potential energy is what is physically important. So that's why where you put the Y equal to 0 does not matter. Because no matter where you put the Y equal to 0, you will get the same answer for the change in the potential energy. I can demonstrate it, but just let me mention it first. So the potential energy is defined only for conservative forces, and gravitational force is a conservative force. Yeah. Given that mechanism, could we find out the potential energy by subtracting that? Yeah, we are coming to that. We are not there yet. First we have to go slowly. Okay, so I am telling you that something called conservative forces, and the conservative forces, when it does work, we do not treat it as the energy is coming from the work done by the conservative force. Instead, we have a different approach. We say, okay, it's nothing about the work done. We forget about the force. We just say there is, because of the force, there's something called potential energy. So instead of the work done, we will solve problem using the energy approach. We are coming to what you're saying. So we are going ahead of me. Okay, so yeah, it's normal, natural. So there can be forces which are not conservative. When the force is not conservative, we cannot attribute potential energy to that force. So we have to, look at the work done by that non-conservative force. Example of non-conservative forces are air resistance, frictions, and so on. So now we got this question. We already answered this question, but anyway, let me repeat. Somebody is telling you the potential energy, absolute value of something is 0. Some object. Now, gravitational potential energy. The equation is potential energy, absolute value is mgy. Okay. So can I tell you where the object is? No. You can say it is at y equal to 0. But we don't know where this guy, whoever told you the potential energy is 0, he didn't tell us where he put the y equal to 0. So that means we cannot tell. Only the person who did the measurements and all, he knows. Okay, we didn't know. He didn't tell me where he put the y equal to 0. So that's why the answer is can't tell. Right. Now, let's imagine now we come to this conservation of energy. If we have an isolated system like system, okay, not just one object, because the object is here and the earth is here. So our system is the object plus the earth, because now we are bringing something called potential energy. The potential energy is coming here because of the interaction between the earth and the object, right? So the system now consists of block that is falling under the gravitational force of the earth. But we forget about the force now, we will just say there is something called potential energy. So if this system is isolated, meaning there are no other forces, no external forces outside of this system, okay, does no work. So if it is an isolated system, there be no other forces on this object. It's a, it's not strictly true. We cannot have an isolated system. Even the moon, which is far, far away, can have a weak gravitational force from the moon on this object. But we will ignore it is very small. There can be air resistance. We ignore that too. So this can be considered to a very good approximation as an isolated system. Then there are no energy coming from outside, and we will say if the system now, as it is now, the initially has a certain total energy, kinetic plus mechanical, kinetic plus potential energy, these are the only energy we can have now, initially, and it is coming down. Here the kinetic energy is zero. Potential energy, we will, what is the symbol we use for potential energy? E potential. It's some value, right? Because it's above the Earth's surface, away from there, it will have depending on where you put the y equal to 0, it may be 0 or maybe some positive value or negative value, whatever. It will have a certain value. Let's say I will say 100 joule. This is 0 joule. Now it is coming down. What happens to the kinetic energy? It will increase. Let's say it comes to let's say this is my y equal to 0. So the potential energy is high. When it comes here, the potential energy is 0. It is initially, it has a potential energy of 100 joule. Now, since I put the y equal to 0 where it is now, the potential energy now have reduced to 0. Where did it go? It transformed into kinetic energy. So that's why as it comes down, its speed increases. So from 0 joule, the kinetic energy has increased to 100 joule. So this is called the conservation of mechanical energy. Yeah.
Would they be in opposite signs?
Outside.
Opposite signs. Like the kinetic energy is positive, so the potential.
Kinetic energy is always positive. It can never be negative, because what is the equation? Half m speed squared. Speed is always a magnitude. It is positive. Yeah. Yes.
Yes, if the objects such as the Earth,
Yeah.
will the kinetic energy be zero?
It will become 0 not immediately upon touching. When it touches, it is not an isolated system anymore. It is interacting with the floor or whatever. It will lose energy later. So that is, I cannot include the time after touching and say it is an isolated system. I limit my duration up to it is touching. When it is touching, it has a speed. Okay, it loses energy. I will just ignore that. I am not worried about what happens afterward. My isolated system is t equal to 0 and until the moment just before it touches. In that period, we have an isolated system. So in that period, we can say total energy, total mechanical energy must be conserved. Okay, so that's why I'm confident if the total energy here is 0 plus 100 is 100. When it come here, the potential energy becomes 0 because that is where I put the y equal to 0. That means where did the 100 joule go? It went to, so the kinetic energy must be, in order to satisfy the conservation of mechanical energy must be 0. Can you say mechanical energy is always conserved? No, it may or may not. If it is an isolated system, within the period we are considering, yes, the mechanical energy must be conserved. So we can write it like this. This is the energy initial, total energy. This is the total energy after. Total energy before is the kinetic energy initial. Kinetic energy initial is equal to half v initial squared, and potential energy initial is mg y initial. Then after, at that point, you say the final, when it is just about to touch the surface of the earth. Or, it doesn't have to be touching. We just say it is in motion. Okay, it is still in motion at this instant. It is not touching, let's say. So we leave that thing out. So at that particular instant, because the potential energy is 0, that means there's a reduction of 100 joule in its potential energy. Where did it go? It went to, it transformed into kinetic energy. Why is it not moving? Okay, right. So this is called the mechanical energy conservation. It is only true for isolated system. That means there is no work coming, no work is being done from outside, no external work. The W there is any external work. And in the absence of non-conservative forces, right? That means there can be other forces, non-conservative forces. Then if there don't exist any non-conservative force, ignore if there is any, like air resistance and non-conservative. If you ignore them, then you can say the mechanical energy must be conserved. So we can put it in this manner. Kinetic energy plus the potential energy is a constant. Okay. In the isolated system, if it has certain value at some initial point, it should keep the same value no matter what happens if it remains an isolated system. Right. This can be written in a different way. That means E kinetic energy initial plus E potential energy initial equal to E kinetic energy final plus E potential energy final. So I can bring, all the final terms together and the initial term together. So you can say that change in the kinetic energy plus the change in the potential energy must be 0. This is the best way to write the conservation of mechanical energy. Only in an isolated system. As long as it remains an isolated system, then we can say this has to obeyed. This has to be obeyed. See, it is like, suppose in our example, potential energy become negative 100, right? It's 100 initially, then it becomes 0. So change in the potential energy is negative 100. What happened? Change in the kinetic energy, it was 0 and became 100. Change in the kinetic energy is plus 100. So minus 100 plus 100 is 0. There can be changes, but whatever the change happened in one energy, if it is positive, the other energy will be the same value with the negative sign. So this is the best way to write as a change in kinetic energy plus the change in the potential energy equal to 0. So I sometimes shift my notation. I sometimes use Ke for kinetic energy. In the book, they use this, but I kind of prefer it, but you should be able to switch between them without any issues. Right. Yeah.
So in the change in the kinetic energy, that can be negative.
Yes. Yes. Change in the kinetic energy. So always kinetic energy absolute value is positive, but the kinetic energy decreases means change in the kinetic energy is negative. Exactly. Right. Now we have a concept question. On the following slide are 5 graphs of energy versus vertical position for an object falling straight down from a given initial height. Which graph represents? We will start one by one at a time. First one. Which one of them represent the potential energy of the object? As a function of what? Potential energy as a function of position, vertical position. You know there is an equation, right? Which is potential energy function is mgy, right? So potential energy is the y-axis, y is the x-axis. Now don't get confused the y, okay? Vertical axis is the potential energy, horizontal axis is the y coordinate. So it's a linear equation, right? Y is equal to, this is a constant time k. So when x equal to 0, y is equal to 0. When x increases, x is the y here, when the y increases, potential energy increases linearly. When it is the same way, but when it goes like that also, when it decreases, it decreases, increases, it increases. It's a straight line because a linear graph. It should go through 0 because when the horizontal coordinate is 0, vertical coordinate is also 0. Y equal to 0, potential energy equal to 0. So kinetic energy should look like that. So this is the graph. So you can see which is the kinetic energy graph. This is the kinetic energy graph. Oh, not kinetic energy, potential energy graph. That's the first question. What is the potential energy graph? What is the next question? What is the total energy graph? It's an isolated system, right? A box is falling, we treat it as total energy does not constant. So what should be the figure? C. So this is the total energy graph. Total. So constant. Right. So some value, whatever the total energy is, the last one, what is the kinetic energy? As a function of y, not as a function of speed. So don't get confused because previously we had a graph, kinetic energy as a function of speed. Now here we want the kinetic energy as a function of y. Which one? This one, or this one? dy, do you say that? This plus the kinetic energy should give you this, right? So only this one, because when the potential energy is 0, right? Total energy is, say, 100. Say this value is 100. So that means at y equal to 0, kinetic energy must be a positive value. This is out. This can be. So we have only these two choices. But total energy is equal to kinetic energy plus potential energy. You know the function of the potential energy. That means total energy should also be linear, because kinetic energy also must be linear, because total energy is a constant. Total energy is a constant. That means this is linear. Kinetic energy also must be a linear graph. So this is how it goes. This is 100, right? So when the potential energy increases, kinetic energy will decrease, such that at any moment this value plus this value should be 100.
Can I say that kinetic energy graph is opposite of potential energy?
Not opposite. I mean, yes, opposite in the sense the sloping direction. Yeah. So when you add these two, you should get a constant. So we know this graph. So suppose at y is equal to, say, 1 meter, the potential energy is, let's say, 50. So kinetic energy when it is 1 meter, this should be also 50. So it should reduce. Okay. As you increase the y, as you increase the y, when the bow goes up, the speed will decrease. When you decrease the y, potential energy will become negative and kinetic energy will become more than 50, or it will increase the other way around. So when potential energy increases, kinetic energy will decrease. So to keep the constant total energy. Right. So here's the answer. Now we come to generalizing this conservation of energy thing. There can be non-conservative forces, right? In an the system can be isolated system, but there can be non-conservative forces like air resistance and friction. So, like this box example that is coming down, if there is air resistance, not all the potential energy is going to be converted to kinetic energy. Some of them will be lost as heat because of the air resistance, okay, because it is a non-conservative forces or friction, air resistance, those things. So it will be losing energy as it is falling. It is negligible, you don't see it is becoming colder or anything. But, if there is lots of high friction, like in a viscous medium or something, it can lose because of the friction or the air resistance. So we will say initial kinetic energy plus the initial potential energy, and there may be other forms of energy, OE, other energy. OE stand for not the kinetic energy, not the potential energy. You can have other types of energy. For example, if you take a human being and you consume food, it creates energy, right? So that can be, or maybe chemical energy, or maybe nuclear energy. And there can be other forms of energy which cannot be put into, of course, potential energy coming from a conservative force. So we can talk about other forms of energy. And you cannot say it is equal to kinetic energy final, potential energy final, and other forms of energy final. In the process of this transformation happening, we can have, if there is any non-conservative forces, it will also take the energy out. So in general, I can write conservation of energy formula like this. So if I take it to the other side, change in the kinetic energy plus the change in the potential energy plus the change in other forms of energy, usually you will say zero, right? Conservation. But if there are other forms of energy, then you call it W, the work done by NC stand for non-conservative forces. Work done by non-conservative forces, usually it is a negative value, right? So it loses the energy. So non-conservative forces, the work done by non-conservative forces is negative. So that's why when you sum up all the changes, you don't get a zero value. There'll be some negative amount which is lost due to those non-conservative forces acting on the object. Okay, so here is a picture that is showing what happened in human. The other forms of energy that we can have is this food energy. Suppose you consume certain food, it creates energy. And suppose you take a food which give a calorie amount of say 100 calorie, you can convert it into joule. Calorie is another unit for measuring energy. It is not the SI unit, but there's a conversion factor. You can convert the calorie into joule as well. So suppose there is a food energy that initially, and let me write that equation. Food energy, say other forms of energy, plus then you have the kinetic energy initial, plus you have the potential energy initial, plus the work done by non-conservative force is equal to, finally, you have other energy final plus kinetic energy final plus potential energy final. Now let's consider a situation where we don't have any changes in the kinetic energy or any changes in the potential energy. If the person, human being, you are talking about a human being, if he is not moving, if he is at the same velocity or he has a zero velocity, then the kinetic energy initial is equal to the kinetic energy final. It will cancel. And again, if he is not moving, it is in the same place, then the potential energy is also not changing, right? Suppose he is in the same y coordinate. So potential energy initial is the same as potential energy final. So you will end up with a simple equation with this condition, which again, if you take it to the other side, you can say work done by non-conservative forces is equal to change in other forms of energy. These are special cases, okay? That is when we are looking at a human being, he is, say, consuming, getting some energy from the food he ate, and is not moving. So changing the kinetic energy is zero, the change in the potential energy is zero. Then the equation that we had, when you write it like this is zero, this is zero. That means then we will get work done by non-conservative forces is equal to change in the other forms of energy. So now we got a question about calculating the weight loss from exercising. If a person who normally requires an average of 12,000 kilojoule, okay, but the normally the food energy is calculated in calories, not in kilojoule. So to get a feeling for that, you can see that 3,000 kilocalorie will corresponds to about 3,000 calorie. And also the calorie also has two things, capital CAL and small CAL. Do you know about this difference between this? Have you heard this before? You know calorie, right? The food energy. Yes. Yeah. Yes. Yeah. 1,000 times more. Small c. Thousands of small CAL is equal to one capital CAL. Yeah. Exactly. So, in other words, yeah, the relationship is one big this is 1 kilocalorie. Big CAL is equal to one small k small CAL. So anyway, that's not that important for us. We just say we will just stick to the SI unit. Say someone, a person, he is normally, in a day, he requires only 12,000 kilojoule. And that means he will use up all the 12,000 kilojoule. If he eats food which gives an energy of 12,000 kilojoule, he will use the whole day, so he has not got any extra calorie. But suppose he consumes 13,000 kilojoule per day, what happens? Every day he will have extra 1,000 kilojoule deposited in his body. So he will gain weight, because the excess calorie will be deposited as fat or liver or whatever, glucose, something. So he will gain weight. So the question is, how much bicycling per day, bicycling or bicycling per day is required to lose this extra energy, which is 1,000 kilojoule. Okay, you need to do some additional work, additional exercise to lose this 1,000 kilojoule every day. He wants to eat 13,000 kilojoule every day. So, but he doesn't want to collect calories also. So he had to lose this extra 1000 kilojoule. And he wants to do it by bicycling. Okay, maybe the stationary bicycling or bicycle. And if, this is in the table, suppose by doing bicycling at a certain rate, he can lose energy at this rate, 400 joule per second. Suppose if you are walking slowly, you wouldn't, maybe it will be less, I don't know. It's just a typical value, standard value from a table. So if you are bicycling, the rate at which you are losing the energy, let's say every second you will lose 400 joule. It is given to you. And use this information to how much bicycling you have to do in a day, how long you have to do this exercise to lose 1000 kilojoule, right? If you do 1 second bicycling, you will lose 400 joule. So it is 400 joule if you do 1 second. So to lose 1000 kilojoule mean 1 million joule, right? So 400 joule, 1 second. 1 million joule, how many seconds? And then convert the second into hours or minutes or whatever. So this is the equation. Power is work divided by time. So power is given to us, the 400 joule. The how much you have to lose is 1000. We have to do this much of work, kilojoule. So you substitute the power 400 joule per second. The work you need to do is 1000 kilojoule. Substitute, make sure everything in SI unit. Is kilojoule SI unit? No. So you have to multiply it by 1000. So 1000 into 1000 is 1 million joule. And for joule per second is SI unit. Then you calculate what delta T. When you do that, you get delta T to be 2500 second. But that doesn't, you don't have an idea, right, in second. Maybe if you give it in minutes, maybe the answer is supposed to be given in minute. So you know how to convert the second to minute? Divide by 60, you get this 42 minutes. Right. So